Welcome to the Discrete Universe podcast.
Great to be here.
Today we're diving deep into something pretty fundamental in physics, gravity, acceleration, and how they relate.
Right, but not just the usual story.
Exactly. We're looking at it through the lens of a fairly radical alternative, quantum geometry dynamics, or QGD. Our mission really is to unpack how QGD sees the difference, or maybe the non-difference, between inertial and gravitational acceleration.
And crucially, how we might actually test that difference. It's not just theory.
Yeah, that's the exciting part. We'll be pulling from various QGD discussions, thinking about some unsolved physics problems, and even touching on Occam's razor a bit.
Sounds like a plan. Where should we start? QGD's core ideas.
Let's do that. What's the absolute foundation of QGD?
Okay, so the big thing, the immediate departure, is that QGD says the universe isn't continuous, it's discrete.
Discrete, meaning like pixelated.
Sort of, yeah. It's built from these truly fundamental particles called preons, positive ones and negative ones. That's it.
Just two types. Wow. So everything, space included.
Well, space itself isn't fundamental in QGD. That's a key point.
It isn't. How does that work? Where does space come from then?
It emerges. It comes from a repulsive force between all the preons. They call it n-gravity.
N-gravity. Negative gravity. Repulsive.
Exactly. Imagine all these negative preons constantly pushing each other apart. The space we experience is kind of the result of all that pushing.
Okay, that takes a second to get your head around. Space from repulsion. So what about matter? Stuff.
Matter comes from the other guys, the positive plus preons. They attract each other through a force called P gravity.
P gravity for positive. Makes sense. So repulsion makes space, attraction binds matter.
You got it. Those two forces acting on those two preon types build everything.
Right. Okay, discrete universe, space, and matter from preon forces. How does anything move in this picture? We think of motion as smooth, continuous.
Another big difference. Motion, at least for the positive preons that make up matter, isn't smooth. It's jumps. Yeah, they call them pionic leaps. Think of it like a plus preon is here, then it's instantly over there, a discrete step.
Like quantum jumps, but maybe more fundamental?
Kind of. And there's a limit to how fast these jumps can happen, how frequently.
Which I'm guessing connects to the speed of light, c?
Precisely. In QGD, c isn't just the speed of photons, it's the fundamental speed limit for everything at this level governing these pionic leaps.
Okay, so c is baked right in. Now, what about energy, mass? We all know E, M is E, but how does QGD derive that?
It actually comes out quite naturally. For one single plus preon, its energy, E, is just its momentum, P times C, EPC.
Right.
Simple.
ETC for one preon.
Right. Now, for an object like this table, or you, the total energy is just the sum of all the EPC energies of its constituent, plus preons, plus, the binding energy holding them together.
And that sum just adds up to EVCR.
Pretty much, yeah. Mass in QGD is literally the count of the plus preons plus their binding energy. Mass isn't some abstract property, it's a count of fundamental particles.
A count. That's
Yeah.
very direct, very concrete. Okay, what about time? That's always the tricky one.
QGD has a unique take here, too. It argues time isn't physical, it's not a dimension you travel through.
Not physical. So what is it?
It's relational. It's basically a way we order events by counting repeating cycles in periodic systems. Clocks.
So clocks don't measure time, they just tick. And we call the counting time.
Essentially, yes. Clocks count events. Time is how we relate sequences of those events. It's a comparison tool, not a fundamental river.
Wow. Okay, let's recap the QGD basics. Discrete universe, preons plus and black. Space from n-gravity repulsion, matter from p-gravity attraction, motion via pionic leaps at speed c, mass is a preon count, and time is just counting events.
That's a good summary of the foundations.
Right. Now, to really understand QGD's view on gravity and acceleration, maybe we should quickly touch on the standard picture first. Like Newton and Einstein.
Good idea. So Newton had inertial mass resistance to push and gravitational mass, how strongly gravity pulls. Empirically, they seemed identical.
And Einstein took that further with general relativity.
He did, with the equivalence principle, which basically says you can't tell the difference between being in a gravitational field and being in an accelerating frame, like an accelerating rocket.
The classic elevator thought experiment. Gravity feels just like acceleration.
Exactly. It's a cornerstone of GR. They are treated as fundamentally equivalent.
Okay, so that's the standard view. How does QGD challenge this equivalence? Where's the split?
This is where it gets really interesting. QGD agrees that gravitational interaction, say, between the Earth and an apple, involves changes in momentum. Specifically, the momentum vectors of the apple's constituent plus preons change due to interaction with the Earth's plus preons.
Okay, changes in preon momentum. Sounds reasonable.
But QGD says the cause and nature of this change is fundamentally different from what happens when you just push the apple, apply a non-gravitational force.
How so?
QGD also talks about something called metric velocity. It's a bit complex, but think of it as the preon's true absolute motion in the discrete background, separate from our relative measurements.
An absolute velocity, that's different.
It is, but the key distinction for acceleration is this. QGD claims gravitational acceleration is inherently independent of the mass of the body being accelerated.
Like we observe, things fall at the same rate.
Right, because gravity, in QGD, acts individually on each plus preon within the object. More mass just means more preons, but each one responds the same way to the gravitational interaction.
Okay, so gravity acts per preon, making the total effect mass independent. What about non-gravitational acceleration then, like pushing something?
That, QGD argues, is mass dependent, just like good old FMA or FFM. If you apply the same external non-gravitational force F to two different masses, the acceleration is inversely proportional to their mass.
The lighter one accelerates more.
Exactly. So gravitational acceleration is mass independent. Inertial non-gravitational acceleration is mass dependent. That's the fundamental split QGD proposes.
That's a direct contradiction to the equivalence principle, at least in its strictest sense.
It is. And QGD suggests this difference isn't just theoretical, it might be testable.
Okay, how? I know there's some thought experiments involved.
Right. Let's walk through them. First, the green room at rest. Imagine a sealed room just sitting on Earth, normal gravity.
Right.
You have two spheres inside, maybe one lead, B, one aluminum, A, different masses. You drop them.
They fall together, hit the floor at the same time. Standard gravity experiment.
Exactly. Both accelerate downwards at G. This matches Newton, Einstein, and QGD's view of pure gravitational acceleration. It's mass independent.
Fine. Now the second one. The red room accelerating upwards.
Okay, now imagine the same room, same spheres, but it's in deep space, being pushed upwards by a rocket accelerating constantly with force F.
So an accelerating frame mimicking gravity.
Right. An observer inside drops the two spheres again. They see them fall towards the floor. But here's the QGD prediction. The heavier sphere, B, will be observed to accelerate towards the floor faster than the lighter sphere.
Wait, the heavier one accelerates faster relative to the accelerating floor. Why? That seems totally backwards.
It does seem counterintuitive based on gravity, but remember, the room is being accelerated by a non-gravitational force,
Yeah.
F. According to QGD, non-gravitational acceleration is mass-dependent, AFM.
Okay.
When the spheres are released inside the accelerating room, they're no longer directly pushed by the floor. They essentially want to continue at the velocity they had, but the room keeps accelerating upwards. The floor rushes up to meet them.
Right.
But the key in QGD is that the room's acceleration is related to its mass, or the force needed.
Wow.
When the spheres are let go, the apparent downward acceleration relative to the accelerating floor depends on how effectively they resist the change from being accelerated with the room to being at rest relative to the initial frame. The heavier sphere has more inertia, more plus preons resisting change.
Still trying to visualize that. So the room accelerates up. The spheres are released relative to the room.
Okay, let's refine that explanation slightly based on the source's reasoning. The source suggests that when the non-gravitational force F accelerates the room, the internal effect on the released spheres isn't equivalent to gravity. The apparent acceleration towards the floor, as seen by the observer in the room, arises from the room accelerating away from the spheres. But QGD posits that this non-gravitational scenario would reveal mass dependence. The heavier object B would appear to accelerate faster towards the floor than the lighter one A.
Okay, so the difference in apparent acceleration is the smoking gun that tells the observer, I'm not in a gravitational field, I'm in an accelerating box.
Precisely. That mass-dependent difference in acceleration is the signature, in QGD, that distinguishes non-gravitational inertial frame acceleration from true gravitational acceleration.
Fascinating. What about the third one, the elevator cable snapping?
Right. Before the cable snaps, you feel your weight because the elevator floor exerts an upward contact force, H, counteracting gravity. That's a non-gravitational force.
Okay.
Cable snaps. The non-gravitational force H disappears. Now only gravity acts. What happens?
The elevator and you both fall freely at G. You feel weightless.
Oh, exactly. Both you and the elevator accelerate downwards at the same rate, irrespective of your masses, because only the mass-independent gravitational interaction with Earth's preons is acting. The contact force is gone. This aligns perfectly with QGD's view of pure gravity.
So the green room and the falling elevator show mass-independent acceleration, gravity. The red room shows mass-dependent acceleration, non-gravitational force. That's the core distinction QGD is making.
That's the crux of it. Gravitational acceleration affects each preon equally, leading to mass independence overall. Non-gravitational forces lead to mass-dependent acceleration, AFM.
And the red room experiment, detecting that difference in acceleration between the heavy and light sphere, that's the potential test.
That's the proposed experimental signature. If you could build a perfectly isolated accelerating frame, shield it from external gravity, and measure precisely enough, QGD predicts you'd see heavier objects accelerate slightly differently than lighter ones relative to the frame itself. Something GR's equivalence principle says shouldn't happen.
Yeah, I can immediately see the if you could build problem, isolating from gravity perfectly, measuring that accurately. That sounds incredibly hard.
Oh, absolutely. Monumentally difficult. Gravitational gradients, frame imperfections, the practical challenges are enormous, but theoretically it provides a clear point of divergence.
It's a potential crack in the equivalence principle, at least as we currently understand it.
A potential crack, yes. Or perhaps a deeper understanding of what equivalence really means at the quantum level.
Does QGD make other predictions that are maybe easier to test? Or just different from standard physics?
It does propose a few other things. For example, it suggests tiny asymmetries might exist in electromagnetic forces under certain conditions. It also offers an explanation for dark matter.
Oh. What's dark matter according to QGD?
Free positive plus preons, just unbound matter particles drifting through the emergent space.
So not some exotic whim, just more the basic building blocks.
Essentially, yes. And it offers alternative ways to think about things like relativistic effects, suggesting it's the clock mechanisms physically slowing down, not time itself dilating.
Ah, back to time being non-physical.
Exactly. And the uncertainty principle isn't fundamental randomness, but a consequence of discrete momentum and the fact that measuring inevitably interacts with these discrete preon states. It even suggests explanations for dark energy based on preon dynamics.
It sounds like a very ambitious framework, trying to rebuild physics from these discrete preons upwards, addressing consistency issues maybe that plague the standard model and GR.
That seems to be the goal. The sources mention looking at foundational issues, like Hilbert's sixth problem about axiomatizing physics, suggesting QGD aims for a more logically consistent starting point, avoiding some paradoxes or tautologies found in current theories.
So we have the established, incredibly successful equivalence principle, but QGD comes along and says, hold on, there's a subtle difference here between gravity and inertia, rooted in the discrete nature of reality, and maybe, just maybe, we can test it.
That's a great way to put it. It forces us to re-examine our assumptions about continuity, about the nature of force, mass, space, and time.
This deep dive really shows how thinking differently about the fundamentals, like what if the universe is discrete, can ripple outwards, offering new explanations and, crucially, new potential experimental questions.
Absolutely. It makes you wonder, could we actually perform that red room experiment one day? What level of precision would we need? And could this kind of discrete approach be the key to unifying gravity with quantum mechanics?
Big questions. Definitely something for our listeners, especially those with a physics background, to chew on. Could QGD, or something like it, be a path forward?
It's certainly a path worth exploring, even if just to challenge our current understanding.
Indeed. Well, this has been fascinating, a real glimpse into a different way of seeing the universe. We encourage everyone listening to think more about these ideas and join the conversation.
Thanks for exploring it.
Thank you for taking this deep dive with us into the discrete universe.